Thanks everyone for being here. Welcome to the last day of PyData Global. For the next 30 minutes, we will be talking about active preference learning and optimization under uncertainty. So let's jump right into it. First of all, who am I? My name is Quan. I'm a PhD student, and my research focuses on Bayesian methods in machine learning and decision-making under uncertainty. So that's the big umbrella that our talk falls under. So I'm pretty excited to be here. I also sometimes write about Python programming, and you can find some of my books online, including Advanced Python Programming and the Statistics and Calculus Workshop. Here are my social media links. If you go to my GitHub profile under the talks repository, you'll be able to find all of the code that I use to generate the plots that we'll be seeing throughout this talk. And there's also a link to the slide deck that we'll be looking at. Also, just a quick note, if I do badly on time, we might not have time for questions during the talk. So feel free to add me in this talks channel on our Slack workspace. My username is just Quan Nguyen, my name. So yeah, definitely, if we don't have enough time for questions, definitely let me know on that Slack channel. So with that, let's get started. So I want to spend a couple of slides motivating the problem that we're solving, which is black box preference optimization under uncertainty. And this is a very common problem. The general setup is when you have a combination of parameters you want to tune, and you want to optimize a user's preference function. For example, if you're Facebook or Meta, as they just recently changed their name, you might want to tune the frequency at which you display ads to your users' newsfeed so that you maximize the probability of them clicking on an ad. A completely different example is if you're a 3D animator and you're working with a client and you are tasked with creating a very expensive 3D rendering of an object, and you have some parameters to tune, such as the smoothness or the coloring of the object. So you have to find the best combination for those parameters to meet your client's expectation. And it doesn't have to be a product recommendation company trying to optimize your preference either. It could just be you trying to optimize some process, some procedure on your own. A fairly common example here is optimizing some recipe for a dish or for a drink, and finding the best amount of sugar to put in coffee will be the example that we will be coming back during this talk. So formally, the setup of this problem is that we are given access to a user's preference function f, which we also sometimes call the objective function that is defined on some domain D. And our goal is to find the global optimum of the function x star here that maximizes f over the domain. But there are a couple of challenges that we have to face. The first is that f doesn't have an analytical form, or sometimes we don't have access to it. So we don't know how the generating the process of the function values f of x is being generated. And another challenge is that obtaining function values is expensive, either in terms of time or money or some other safety critical condition. Another unique challenge that is the defining feature of this preference optimization problem is that function evaluations only come in the form of pairwise comparisons. So the user doesn't actually rate a product they are presented to on a scale, but instead they are presented with a pair of products, and they have to report back to us which one they prefer more. So in this example, if they're presented with two products, X1 and X2 in the domain, then if they prefer X1 over X2, they would say f of X1 is greater than f of X2. We see that this pairwise comparison data is more natural and easier to survey than real value ratings. And indeed, research has shown that humans are way better at comparing items rather than rating them on a scale. And we can come back to this example of trying to find the best recipe for coffee, say, our preference might change from day to day. So our real value rating for a given cup of coffee might change from between today or tomorrow or the day after. But we can be fairly confident that if we prefer this one cup of coffee over the other, then that will stay very consistent. And this is the exact problem that some product recommendation researchers and engineers run into, where they ask their users to rate the product on a scale, and they have to assume for a considerable level of noise. But if we design our system so that it can handle this kind of preferential pairwise comparisons, then we can be more confident in the quality of the data that we are collecting. But we could also reduce the cognitive burden from the user, which is also a nice added bonus. So the real question is, how could we design such a system so that it could work with pairwise comparisons and help us identify the best product that maximizes a user's preference? And that's what we will be learning to do in this talk. So how does this look? Big picture, we will start out with a machine learning model that could be trained on pairwise comparisons. And we will use this model to suggest new products to the user. After analyzing the product, the user will report back to us their preference in the form of pairwise comparisons. And then we will add this new data point to our running training data set, and the model will be updated on this data set. Again, the goal here is to find the best product that maximizes the user's preference, and we repeat the whole procedure until we reach some termination condition. We will be focusing on two main components. The first is the machine learning model that can learn from preferential data, as well as the mechanism we use to suggest new products to the user, which I typically call the optimization policy. All right, so to make our discussions more concrete, we will be using a running toy example. The question we ask ourselves is, how much sugar should we put in a cup of coffee so that we maximize our preference? So in this case, the function f, the objective function, denotes our utility while drinking a cup of coffee with X grams of sugar in it. Health experts claim that we should not have more than 25 grams of sugar in a cup of coffee. So that would be a domain from 0 to 25. Note here that f is just a one-dimensional function, where x is the amount of sugar. But if we have more parameters to tune in this procedure, for example, if we want to jointly tune for the amount of milk to put as well, then it would be a two-dimensional objective function. But again, we assume that we're only working with sugar for now, so it's a one-dimensional function. So what does this f look like? It could be plotted as a graph where the x-axis is the amount of sugar and the y-axis is our utility. If you have a sweet tooth, then your utility might linearly increase with respect to x, and your preference is optimized with maximum x. In this case, it's 25. If you have the opposite preference, then your utility might decrease with respect to x. For most people, their utility is optimized at some location in the middle. And as you move further away from this location, your utility will decrease. For some other people, their utility might look even more complicated with many local optima. So in this example, this person prefers 5 grams of sugar or 20 grams of sugar over the other points in the domain. We will be using this function as the true objective function that we are optimizing when we come back to this example later on. But again, in our setting, we assume that we don't know what this function f looks like. And our goal is still trying to find the X star that maximizes it over the domain using only pairwise comparisons. At this point, I should stop for any immediate questions, but I'm running low on time. So please note down your questions on Slack or maybe on Zoom. Okay, so moving on with the talk. Remember, in our learning loop, we have two components that we need to design. The first is the machine learning model that learns from pairwise comparison data. In this case, we will use a Gaussian process or a GP. Overall, a GP defines a distribution over functions, and it generalizes the concept of a normal distribution for a random variable to functions. So how does this work visually? Usually we start out with a constant GP across the whole domain before observing any data. The solid line here is the mean function, and the shaded region is the confidence interval. And the way we usually read this plot is if we were to take a vertical slice of the plot at any given point, we will obtain a normal distribution representing a belief about the function value at that point. So for example, if we care about what f of 7 is, what we should do is to take a vertical slice of a plot at 7, and we will obtain a normal distribution where the mean of the distribution is the intersection of the vertical slice with the mean function here mu. And the standard deviation is simply half of the confidence interval. I see there's one question in the chat. The moderator, please let me know when we start for question later.
Sure.
But thanks for the question. Okay, so at this point, we haven't observed any data yet. So the GP is just constant everywhere. So nothing interesting is happening. If you have worked with a GP before, you might know that with real value data, such as some f of x is equal to some y, then we can efficiently update a GP exactly. But remember that in our setting, we are working with pairwise comparisons. So our data actually comes in this form. Unfortunately, a GP cannot be exactly updated on this kind of data. But in Bayesian statistics, there's a trick called Laplace approximation that could help us with this. We will not be going into the math of Laplace approximation, but the idea is first, we compute the probability of the data that we are observing. So in this case, we're observing this data point, and we are computing the probability of f3 is greater than f of 12. And what we do with Laplace approximation is to manually tweak the GP so that it maximizes this probability. Visually, it will look something like this. Pretend that, again, we are starting out with a constant GP that's just 0 everywhere for the mean function. And we observe this data point that we've been looking at, f of 3 is greater than f of 12. If we update the GP, the new model will look something like this using Laplace approximation, where the mean function has changed a little bit so that it now has a slightly negative slope to represent the fact that f of 3 is greater than f of 12. Let's look at for more data points. Let's pretend that now we observe f of 12 is less than f of 20. So the new GP updates to this model. If we also observe that f of 3 is less than f of 20, then now the new model becomes this. What's really interesting, I think, about this is that the mean function absolutely obeys all these preferential ordering in the training data that we have. F of 3 is indeed greater than f of 12 here. F of 12 is indeed lower than f of 20, and f of 3 is also lower than f of 20 here, which is very nice. But we also see that the confidence interval around these data points, these 3 data points, have shrunk a little bit to represent the fact that we have learned something about the function values of these 3 data points. I just want to reinforce. Oh, and at this point, our trick with a vertical slice still applies. If we care about f of 7 again, then we take a vertical slice of the GP at 7 and note down the intersection with the mean function and the confidence interval, and that will give us a normal distribution, now an updated normal distribution representing our updated belief about f of 7. Again, at this point, I just want to re-emphasize the fact that this GP is a very nice mathematical object that we're working with, whose mean function conveys all the preferential ordering that we have in the training data. But it also offers a calibrated quantification of uncertainty, which is very important for the downstream optimization task, which we will discuss later. And with this quantification of uncertainty is what sets the GP apart from other point estimate models, such as a neural network or a decision tree. Okay, I think I'm still running a bit low on time, but thank you for the questions. We definitely get to those questions later, but for now, let me just quickly move on to the second part of the talk where we talk about optimization policies, where we use the GP model we have to make new recommendation of new products to the user. Here, this process is typically called Bayesian optimization because the model that we're working with, the GP, is a Bayesian model. Now, a good Bayesian optimization policy should trade off between exploitation and exploration. Here is the GP that we have been looking at. So at each iteration of the learning loop that we saw earlier, we need to ask ourselves the question whether we should present to the user some point where we expect to have a high preference value, such as this point over here. This corresponds to exploitation. Or should we present to the user some point that we don't know much about, such as this point over here where the uncertainty is higher? This corresponds to exploration. So we need to balance between these two aspects of the optimization. A natural approach is to appeal to the concept of improvement. Here, the motivation is the question, how much do we expect to improve from the current best point that we have seen so far, which we typically call the incumbent y star, if we were to query the function value f of x at any given location x. Here, improvement is defined to be this quantity I of x, which is a fairly natural metric for improvement. If f of x is greater than y star, the incumbent, the best point that we have seen so far, then this whole quantity I of x is equal to the difference between f of x and y star. So we improve by the difference. If f of x is less than y star, however, then this whole quantity is 0. So we don't improve by we don't improve from the incumbent. So it's a natural metric to measure the improvement that we could make. But note here that we don't actually know what f of x is equal to. So we don't have a way to exactly compute I of x. But thanks to the GP that we have, f of x actually follows normal distribution with a known and standard deviation. So what we could do is we could compute the expected value of I of x very easily. Visually, it will look something like this. Because we care about improvement from the incumbent, we first need to identify the incumbent, which in this case is this green point. And we only focus on the upper portion of the GP, denoting the improvement that we expect to make. Then we compute this expected value across the domain, which again, we can do fairly easily, thanks to the normal distribution belief we have, which I'm showing here in the bottom plot. Now, the policy resulting from this process, which is typically called the expected improvement policy or the EI policy, will tell us to query this point that maximizes the expected improvement score in this case. So with this expected improvement policy, we have a way to find a point to present to the user in order to find the global optimum. But remember, in our setting, we need to present to the user a pair of points. So we need a way to extend this. Well, the first natural way is to just simply extend our improvement measure to take in not 1 point, but 2 points, x1 and x2 here. And the maximum is defined over the incumbent, f of x1 and f of x2. So we could do that as well. This policy is typically called EI2. But there's also another natural way to extend the old EI policy, and that is to compare the point suggested by EI with the current best point that we have seen, the incumbent. This is actually the strategy that professional photographers use, where they take a lot of pictures of you and they ask you to compare the picture that you like the best so far with the remaining pictures. You can think of this as some sort of a last incumbent standing strategy where you try to beat the incumbent with the point suggested by EI. So this policy, EI incumbent, is the second policy that we could use. So let's look at one example of how EI incumbent works. Let's pretend that during the optimization procedure, this is the GP that we are working with. So the whole process starts where we compute the EI score across the domain. And we first need to find the point that maximizes the score, which in this case is this red point. Then we will ask the user to compare this red point with the incumbent the best point that we have seen so far, which is this green point. Now the user who actually has this orange object preference function that is hidden away from us will tell us that the green point is better than the red point. So we'll update our GP to this new model using Laplace approximation as we have seen. Now we repeat the whole process again in a new iteration of the loop where we compute the EI score, find the point that maximizes the score, and ask the user to compare it against the incumbent, which is this new green point. Now the user will tell us that the red point is better than the green point. So we update our model to this new GP. Do this one more time, compute the EI score, find the maximizer of the score, and ask the user to compare it against the incumbent, and update a GP after observing their pairwise comparison. Now, at this point, we see that our GP models the region around the global optimum fairly well in terms on a relative scale. And in fact, the maximizer of the mean function around here actually corresponds to the maximizer of the true objective function, which is the global optimum that we're trying to find. So just from this one example, it seems that what we're doing is working. But one example might not be enough to convince us that this EI incumbent is effective. So I ran a couple of numerical experiments where I benchmarked the policies that we have across different objective functions. So really quickly, the procedure is something like this. For each objective function that we will see, each policy will start out with the same random data set, and each policy is allowed to make the same number of queries to the user, which is just a simulated oracle in my experiments. And throughout this process, I measure the gap measure, which is like a common metric in Bayesian optimization. We don't really know what it is, but we don't really need to know what it is, but it's between 0 and 1, and the higher it is, the better. And for robustness, I also repeat each experiment 10 times with a different random initial data set. So let's look at some results. Here I compare EI2 and EI incumbent against a naive benchmark, which is just a random policy that uniformly selects 2 points in the domain and present it to the user. Starting out with this.
I'm sorry to interrupt you, Quan. Until now, we just have one comment, no questions, but we have like 3 minutes more. So just, okay. I can remind you.
Thanks for the reminder. I'll try to wrap this up really quickly. So for this very simple function, here on the right, I'm showing the gap measure again as a function of the number of queries made to the user by the 3 policies. And remember that the higher the gap, the better. So in this case, all 3 optimization policies are actually very good. However, if we switch to a slightly more complicated true objective function with more local optima, then the difference between the 3 policies becomes clearer, where the random policy becomes a bit worse and EI2 emerges as the top performing policy. And overall, EI2 is actually the top performing policy for one-dimensional objective functions. However, as we move to higher dimensional objective functions, in this case, we have a 2-dimensional objective function, then the trend becomes a little bit more complicated, where random actually completely fails at this optimization task. It doesn't improve the gap at all. And EI incumbent takes over as a top performing policy. And the same trend continues for other higher dimensional objective functions as well. So at this point, I think we've seen some evidence suggesting that the 2 policies that we have designed, EI2 and EI incumbent, are better than a naive benchmark of randomly sampling. And we have also gained an interesting insight that EI2 is better for one-dimensional objective functions, while EI incumbent is better for higher dimensional functions. So for the last part of the talk, really quickly, I want to touch on some practical considerations you might want to know if and when you decide to implement this procedure on your own use cases. So the first, of course, is what open source packages you could use. The first option that you have is gpro, which is a fairly lightweight extension of scikit-learn. And it uses, as you can see, very friendly NumPy syntax. So it makes it very easy for you to use if you're familiar with NumPy. And its code base also very small. So it's very easy for you to go in here and dig around and see what's going on underneath. But if you want a more heavy-duty streamlined option, then Blowtorch would be your best bet. It's developed by Facebook, or I guess Meta at this point, and it belongs to the PyTorch GPyTorch ecosystem. So it has very extensive support, not only on this preference optimization framework, but other Bayesian optimization framework as well. I have 30 seconds left, so I just want to quickly mention some exciting applications that you could apply this preference optimization framework to. There are many applications such as audio processing and image processing. An exciting application that I think is really interesting is working with deep generated models, where you have a latent space in the middle, and you can use a deep model such as a variation or autoencoder to generate objects. So what you could do is to apply Bayesian optimization on this low dimensional latent space and present to the users generated reconstructed objects at the end here to collect that feedback. Real quick, I'm just going to show this GIF here, where it's just a cool transition of the optimization process where you present images of fashion items to the user, but you can still optimize within a low dimensional continuous space. And that is the end of my presentation. Thank you for being here again. And I think my time has run out, so I'll be happy to take any questions on Slack.